All right, in this video, we're going to look at some of the extra topics that we had to skip because basically the AP exam wasn't going to cover them. And these are topics that colleges will expect at least you've seen before. So we're not going to go into the level of depth that we would have in the AP course because especially this topic, it had a theorem associated with it and a proof of why this worked. I'm more going to try to just give you the big idea of how to do it and a little bit of, as best as I can get, some intuition as to why it works, but try to keep it basic. All right. So this first topic is being able to use integrals to find the average value of a function. This does connect to just finding averages. If you go back to late elementary school or early middle school, someone tells you, here's how you find an average, or AKA the mean. So this is basically the grown-up calculus version of how to do a continuous function and find its average value. All right, so we're going to start off with a simple example and then connect it to the formula. And the formula uses integration. All right, so here's a very simple example. Say this is a bank account, and to keep it simple, say there's a certain amount in the bank account all throughout the month. The person only goes in and either takes out money or puts money in at the beginning of the next month and then leaves it there till the next month. So think of it maybe like a savings account or something. So how would we find the average value of a non-continuous function? This is discrete. It's broken up into 5 solid chunks. It's not one of those smooth, curvy functions. So if you follow the bars and you remember about getting averages, well, the person has different amounts in their account each month, but we could sort of come up with an average amount that's in the account. And in real life, people do this for like credit cards and stuff. You know, the value's changing from time to time. So they sort of go with an average when they charge you interest. So someone might be concerned with what's the average amount in the bank account. Maybe the person who has it's like, on an average, how much money do I have? It keeps bouncing back and forth. Well, how would we calculate an average before calculus? Well, we add things up and we divide. So if we take a look, there's 2,000 in January, and then at the beginning of February it goes up to 3,000, then at the beginning of March it goes down to 1,000, and so on. So there's basically 2,000, 3,000, 1,000, 2,000, and then 1,000. So if we wanted the average amount that was in the account, well, you probably all know how to get averages. You add things up and divide. We would add up all those totals and divide it over the 5 months that are there, and there would be our average amount. So over the 5 months, this was the complete total of those 5 months, divided by 5 into sort of 5 equal pieces, and it distributes everything out nicely. That on average, there was $1,800 a month in the account. All right, so we want to extend this process because basically, how do we do this for a continuous function? So the problem is we still want to be able to add and divide. Now, how is this connected to calculus? Well, we've been talking integration, and integration is the area under a function. So in this case, this is a discrete function, or non-continuous, where it's just these blocks. If we wanted to think of it from an integration perspective, the calculation below is equivalent to finding the area under here. Basically, the area under here accumulates the money, accumulates the y values or outputs of the function. But we don't want their total accumulated value. We want it broken up over the 5 months or averaged. So what we would have to do is basically add all this area up and then divide it by how wide this interval is. This interval is 1, 2, 3, 4, 5 months wide. So if we know from start to finish that this is 5, we can add all this up and then divide it into 5 equal pieces, and it'll basically give us, as if these were all leveled out, what is the average y value or average money value that's in the account over those 5 months if it was all evened out. All right, so what that amounts to is finding this area. Now, we essentially did that in our calculation because these are 1 month wide and like 2,000 tall, 1 month wide, 3,000 tall. So we could think of each of our entries below as an area. This is the total accumulated area up top, and then it gets divided by the width of the interval. So in a more grown-up fashion, if we have a continuous function, it sounds like integration would do the same thing. Integration would sort of add up all the changes of the y values, and then we would just have to divide by the change on the interval. Now, let's look at maybe a little more realistic example of what happens in the bank account. Say these red dots represent what's happening really to the account. Someone's going in every couple days now and making either deposits or withdrawals. So for some reason, this amount's going up. They're putting money in. They're putting money in. Now money's coming out. Now money's going in. Now money's coming out. This is more realistic of what would be happening. Now, we could make a whole bunch of bars and divide them up. But what we could do with this is if we could find a continuous function that approximated this really well, or in real life, some functions they're naturally defined to be continuous. So if we had some continuous function we wanted its average value, we could basically add up all the area under the curve that's taking its integral and still divide it by the width. So we'd still divide it by 5, but I'd integrate whatever this function is, and this function's more complicated, but integration will take care of it for me. Like I said, if I can do it by hand, I could do it with an antiderivative. If not, I could pop in a calculator. All right, so the idea for finding the average value for something that's either, basically if you have a continuous function that can approximate this, or you have an actual continuous function, is to integrate it and then divide. All right, so this is how we get the average value of a function, or think of the average value as the average output or average y value, because the y values are changing. Now in a continuous function, like we're going to look at below, the way we're going to think of that average output is that it's the average amount of area per unit. So basically we can find the total amount of area and then just divide it by the number of x units that we've crossed. So if we were looking at this example, now this is a continuous function, this is a polynomial. If I wanted the average value on this interval, let's give these numbers. Let's say it's 2 to 10, just making those up because they have them labeled as A to B. Let's say they're 2 to 10. If I wanted the average height, so this would be a lot harder to do because this y value is changing all the time. There's an infinite number of values between 2 and 10, and this thing is starting out high, and then it goes low, and then it comes back. So you could picture that there's some average y value. Like this value is too tall to be the average because it's the maximum. This one's too low. Somewhere maybe around here, there would be this y value that was the average of all these fluctuations. So the way we're going to be able to get that average output is essentially to find this area like we did before, but break it up evenly over the interval. Now, since I said it goes from 2 to 10, there would be 8 units. You'd have to go, well, this is 8 units wide. Then what is the accumulation under this function over time? How much does it get, or over whatever this x value is? How much is there in there total? Well, the integral gives that to us. So if we integrated from 2 to 10 of this function, we would get that total amount, and then we would just have to divide it by the width of the interval. Well, the interval is 2 to 10. 10 minus 2 would give me 8. So if we integrated and divided this by 8, it would give us the average value. And it would give me, basically, what I would get would be the number that, if I put it on the y-axis and sort of drew a line, it would be the y value that would even this thing out. It would be the height that this thing had on average. All right? So the way they write is, even though the integral covers because when you do an average, you're adding and dividing. The integral covers the adding, and then we'll put a little fraction outside to cover the dividing. So instead of dividing, they just put it as multiplication by the reciprocal. So I would put like for this, if I was going from 2 to 10, it was 8 units. I would just take 1/8 of that area to get what the average height was. All right. So let's look at the actual formula. So hopefully now that you have a basic intuition for it. Like I said, I didn't prove any of this with fancy methods, but think of it as a grown-up version of adding and dividing. This says that if f is a continuous function on the interval a to b, then what is the average value, or sometimes they call it the mean value, of this function on the closed interval from a to b? Well, it's defined as this calculation. So like I said, think of this part as adding up everything in the function, and think of this part as dividing to average it out. So the b and the a are the start and end of your interval. And then notice, like, if you've been following this calculus stuff, sometimes we integrate the derivative or do something else. In this case, we're actually integrating the original function, right? So if you want the average value, you're integrating the function that you got. You don't have to do a derivative or anything like that. So integrate the function you got. That'll accumulate the y changes, and then just divide over the change in x, and that basically gives you the average value of y per unit of x. All right. So this formula, a lot of times it can be calculated by hand, but most of the time you can just throw this into a calculator, right? If you just know the format, how to set it up, you're going to integrate your function and then just put this division out here, or this multiplication by the reciprocal. All right, so I'm going to show two examples. One is just purely, let's get the average value of the formula, and then the second one will have a context, because it might be nice to know who uses this stuff. Average values come up in a lot of cases in real life. So you can think about, people care about average money, they care about average population. You might care about the average rate of a reaction in chemistry, or any number of things. So if you need the average output of some function, and the function is continuous, meaning you got infinite values of change, what's nice is you couldn't have done that in middle school. You could be like, oh, let's add up infinite values, but integration essentially covers that for us. So this calculus method allows us to find average value of any function, even something that's smooth and continuous, instead of doing just several values like you would have in like late elementary school or early middle school. All right, so let's see how this plays out. So this first one, I have it almost all worked out. I just don't have the answer up. So it says find the average value of the function f of x equals x to the 1/2 on the closed interval from 1 to 4. X to the 1/2 is the square root function. All right, most of you probably know that. So we want basically what is the average height of the square root function on the closed interval from 1 to 4. Just get a little intuition for what the value should roughly turn out. Well, the lowest the square root function gets, when you plug in 1, square root of 1 is 1. So the lowest y value is 1. Square root of 4 is 2. So the highest y value is 2. So if the function ranges from 1 to 2, the average is going to be somewhere in between. So when we get the answer, we should get something that's between 1 and 2. And the square root function is on the rise. It curves a bit. So it's not going to be perfectly like 1.5 or something, but it's going to be somewhere probably close to that. It'd probably be more biased toward the 2 value because of the curvature. It curves, it's concave down, but it's sort of, more on it has more of the higher values than the lower values in that section. So instead of trying to guess what it is, here's how we calculate. So what is the average output of the square root function on that interval? Well, here's the formula. You just need to know what b and a are. Well, there's your a and there's your b. And you just need to know what the function is, so it's the square root function. So I just plug these things in. B is 4, A is 1. Same thing here. B is 4, A is 1. And the function I'm talking about is the square root function. This gives me the average value. So essentially this is going to add up those like infinitude of y values that are in between here and accumulate them for me. And then we'll divide it by the width of the interval. The interval is 3 wide, so we want 1/3 of what we found. So once again, it's just like regular averaging. It's adding and dividing, but sort of an adult version of it. All right. So how does this come out? And once again, you can do this by hand, but you can also throw it into a calculator, right? That you can't get the antiderivative of this and use the fundamental theorem of calculus. But if you throw it all in a calculator, I sort of did it piecemeal to sort of show the concept. Here's the accumulation of the function. The area here is 14/3. But then you want to take 1/3 of that. So 1/3 of 14/3 is 14/9. Or roughly about 1.55. It's actually 1.5 repeating. I just truncated. I guess technically I should have rounded up to 1.56 if I wanted it, rounded to the nearest hundredth. But regardless, I just put this out here to get a rough idea to see if it makes sense. So what is the average height of the square root function on that interval, or its average output? It's roughly 1.55. Or if you want to be more precise, it's 1 5/9. All right. So this is just a standard example mathematically of, hey, look, we found the average. Let's do one that at least is in context. So if you ever see it again, you know what it's used for. So in this case, we have a context. We're looking at the population of the town of Bigny. Ooh, that's just a coincidence. It wasn't like that town was named after anybody. So in the town of Bigny, they have a model for the population. So the population could be modeled with this equation. It's a exponential growth equation. And basically, this equation is valid from the year 2010 on. So time t is measured in years from the beginning of 2010. So that means time 1 is the beginning of 2011, time 1.5 is the middle of 2011, and so on. All right, so this is an exponential growth equation. And if we think of time 0, which is 2010. So times 0 is 2010. If we plug 0 in here, we can get any value. If we plug 0 in, the population of Bigny in 2010 was 5,000. Now, it's growing, so it's going to be different in 11 and 12 and so on. Now, they want to know what is the average population of Bigny according to this equation from the start of 2012 to the end of 2016. Now, this is why I wanted to kind of do one in context, not just to show you an application of it, but to be careful when you read things. Because if you just read 2012 to 2016, you might think, well, I should use t equals 2 and t equals 6. But that's not actually the case, because this is the start of 2012. The start of 2012 is 2 years after the start of 2010. But the end of 2016, basically the very, very, very end of 2016, is essentially the very beginning of 2017. So the very end of 2016 is happening 7 years after 2010, because basically it's 11:59 and 59 seconds on December 31st, 2016. It's essentially the beginning of 2017. So this is going through to the 7th year, the start of 2017. So just be careful that you get the right interval. I actually want to go from time 2 to time 7 on this. Now, I could find what was the population at time 2 and what was the population at time 7. Should be greater than 5,000. Probably not too much greater. It's only growing by 5%. But basically, I want to know what's the average population. So we should get something probably in the 5,000s. Let's see what happens. In order to use the formula, I want the average value of the population. So I'm just going to plug in the values. Now that I discerned what A and B are, well, I'm going to do 1 over B minus A. So remember, this is a 5-year span. So I want to take 1/5 of what I find. It's part of the average, and I need to accumulate what all that population was from 2 to 7. Well, I'll integrate from 2 to 7 of that function. So this is the setup for your average value, and it'll give me the average population from 2 to 7. Like I said, if I was the Census Bureau or something, I might care about how many people were living in this place on average. Now, I rounded it because I got 5,256. I think it was 0.3 something or other. It's a math model, so is this thing going to exactly model it? No, but as long as it's pretty close. If this is accurate, I did round it down. Obviously, it was 0.3, so I would have anyway. Even if it was like 0.7, I'd probably still round it down, because if I have 0.7 person, I don't quite have the next person yet. So roughly, it's 5,256 people on average lived in Bigny, and that makes sense from what we know of the function. So this would be the average population of this village during that 5-year span from the start of 2012 to the end of 2016. All right, so there's lots of stuff that can be done with this formula. Hopefully you just understand the mechanics of it, that you're just plugging into that formula, and it basically chunks out the average Y value for you. All right. So if you ever see it again, physics, chemistry, business, whatever, it crops up in a lot of places. Especially when you have a continuous function, you can't do it the elementary school way. You gotta update your knowledge and use something that's more powerful. All right. So the assignment is attached to this. Should be pretty simple. You can use the calculator to do it. If you have this formula, it shouldn't be too bad. So give it a try, and see you in the next video.